So, ladies and gentlemen, I just want to make sure that everybody's good with this. Again, I apologize for the typo. I noticed it when I was putting in the answers that these should be chapter 6 homeworks instead of chapter 4. We already did chapter 4. Okay. Nothing else changes. I just typed in the wrong number there. Do be aware when you're doing your homework that you're doing questions from the right chapter. Okay. It is a little bit funny and I apologize. It's just that the way that this all makes sense in my head and the way that it makes sense in Paul Hewitt's head is not the same. So I'm trying to kind of mesh them as best I can, okay, for my logical sanity and hopefully yours as well. So I'm going to go over questions that you have from the homework that I stamped today. And then just a reminder that over the weekend, and we might have a little time at the end today, depending on how things go, to get some of this done, but these will be due on Monday. The big question, there was a question right before class, when are we going to do another lab? Because it's been forever, right? You just feel like you've been sitting there going, oh my gosh, gotta do physics. We're going to do a lab on Monday and Tuesday of next week, we'll do a lab. Okay. So, and then that'll be the lab, that will be the only one for this part, but then in the second part, we've got a few things too. So we've got some hands-on stuff coming up in just a little bit. Life is good? Questions on homework? Yeah.
Number 21.
21. Let me get myself a new page here. And I need to get my book open as well. This is chapter 2, right?
Page 25. Or I guess you have a different book.
No, I have your book. I only look at that one when I need to verify things, but I do that rarely. And 26 was the other one? Any others that you want to put on that list of things to talk about? Cool. So out of a big list, we only have a couple. That's good. All right, 21. This was the ranking one, is that right? Yeah. So blocks A and B are supported by the table, and block C is partly supported by the table and partly by a rope, because that's what we do sometimes, I guess. Rank the support forces. So there, what kind of force are they really talking about? The normal force, right? Does that make sense? It's just another name for it. Yep. Provided by the table from greatest to least. So let's just look at it. And this may be taking it like a step simple, but just it's better to keep it simple than make it more complicated, right? So for A, you have a 10 Newton box. So when it says a 10 Newton box, what is that measuring? What's that? It's weight. Yeah, that's exactly right. The 10 Newtons is its weight. Which means that if we were going to draw a Freebody diagram, we could have a force coming down this way, right? The force of the earth on the box. And we would know that that one is equal to how much? 10 Newtons. Is that okay? Are there other forces acting? The upward force, that's the one that they're asking about, right? Yeah, which is, I don't mean that in a, like a snarky way, just in a, like, we just gotta kind of put this all together, right? So we've also got a force up. That's the force of the table on the box. That's the one they're asking about. That's the one that yesterday we started calling the normal force, okay? They call it in this question the support force. I don't know why, but that's just what they decided to call it. Question for you, ladies and gentlemen. What is the net force or the total force on this box? 0. How do you know that it's 0? Say that a little louder. I think I heard what you said, but I'm not sure.
I said because like one is going up, one is going down, so it cancels out.
Let me ask a question. If you have a force going up and a force going down, will it always cancel out? Not necessarily. There's something special about this situation that tells us that the net force or the total force is 0. It's, say it loud. It's not moving, which means that it's not accelerating, which means that the net force is 0. I'm going to write that down again, and you might want to write it down again too. Have you noticed that I keep repeating it? Probably because it's important, right? So it's not moving, which means that it's not accelerating, And we are just as smart as Isaac Newton, so we can tell ourselves then that that means that the net force or the sum of the forces acting on that box must be 0. Okay? These two things are Newton's first and second law in one case. This thing right here, that's a summation. So it's the Greek letter sigma. Okay? And it means the sum. It does kind of look like an E, true. And I write it kind of fast because that's just, yeah. So it's just like a pointy, it's got a pointy middle part to the E. Yeah, yeah. But it means the sum of the forces. Okay? I'm glad that you asked about this question because there's a word that I wanted to introduce and I forgot to introduce it yesterday that you will need on your homework for tonight. So I want to make sure that I introduce it, and this is a perfect opportunity to do that. Okay? There's another thing that we can call a situation when the net force is 0 and the total forces, are all the forces added up together are 0. It starts with an E. Does anybody know what the word is? It starts with an E. Equilibrium. Yeah. Because you didn't want to what? Oh, no, it was right. You should go with your gut. Yeah. Equilibrium. Have you heard that word before?
Yeah.
Yeah, if something's in equilibrium, it's like balanced, right? Yeah, yeah. Equilibrium means that the forces are balanced. Oops, R. Or you can say that the net force, the total force, is equal to 0. Okay? It's just another way to describe the situation. The box isn't moving? Oh, well, that means the box is not accelerating, which means the net force is 0, which means that it's at equilibrium. It's a big word with lots of I's in it, but it's not scary, right? It makes us look fancy and smart to say equilibrium. So anyway, just wanted to put that out there. So anyway, let's go back to answering 21, shall we? Yes, please. The total force is 0. We know that the one pulling down is 10. So what does the one pulling up have to be, or pushing up have to be? 10, right? That's pretty simple. There's a lot of good physics in there, but it's pretty simple. So that was letter A, situation A. The normal force is 10 newtons. B looks very similar to A. B looks like it's just the same box that was turned on its side. So for example, instead of having the book sitting like this, I'm going to put the book like this. Let me ask, when I put the book like this, laying flat on the table, versus putting the book like this, standing up, has the weight of the book changed? No, I didn't like rip pages out in between, right? So the mass is the same, and if the mass is the same, then the weight is the same. And if the weight is the same, the force of the earth on the box is the same. Tell me about the normal force, the force of the table on the box. Say it with confidence. 10 newtons, it's the same, right? Is that okay? Yeah, so A and B are both 10 newtons. C was weird, right? Yeah, you're probably like, man, why is she even talking about this? Because there was some other stuff I wanted to talk about too, so it was like just perfect timing. But let's go to it. So A equals B, because they're both 10 newtons. C is a little bit funny, yeah? Yeah. How many of you all take your boxes and you put them in equilibrium in such a way, right? Like, who does this? I don't know. Paul Hewitt does this, I guess. I'm going to take my box and I'm going to put it just a little bit on the table. Then I'm going to use a spring scale to hold up the other side because, why not, right? Let's put a little droop, droop. And then we're going to hook that to the ceiling. So that seems convenient. I'm going to start decorating my house like that. All right. And this thing, it said pulled up with, yeah. Yeah. And I just noticed that I had an error. So I want to change that before I get in trouble. That box is bigger. It's double the size. Now I can absolutely scroll up that far. Okay. Yeah. So I got a 20 Newton box. can we draw a Freebody diagram for that one? Is that okay? Tell me about the forces acting on this box. This is a fun box. Do you know what's one of the forces acting on that box?
Gravity. So
Gravity.
Force of the earth on the box.
On the box. And where does that pull?
Down.
Down. Straight down, right? Force of the earth on the box. We can remind ourselves so that's the force of gravity. You don't have to have that FG in there. I just like to remind, it's just helpful. And how big is the force of gravity in this case? I want to know how big the force of the earth on the box is, the force of gravity on the box is. 20 newtons or no? Gerald's putting that out there. What do you guys think?
That's what I was thinking.
Yeah? Magda, what do you think?
Sure.
Because she doesn't want to fight with anybody today. So, I don't know. Other people think? What do you think?
I mean, just all of it isn't on the table. Half of it, like 75% of it, like just in there.
Just hanging there, right? But does the weight of the box, does the force of gravity, does the earth on the box change based on where it's sitting?
No.
No. The only thing it depends on is where it is. It's on the earth, right up near the surface of the earth, and it's got a certain mass. So the weight of the box, the force of gravity of that box is going to be 20 newtons. So that's all we got, right? That's one force. Question for you. How many forces, how many pushes or pulls are acting on this box?
3.
Are you sure it's only 2?
3.
Maddie says 3. Gerald says 2. 17? 37?
No, not 17. I said 10.
I'm just seeing where we can go here.
I said 10.
You think, okay, so I think there's more. Okay, so there's more than one. Because we know that they want to know about the force, the support force, right? The support force is the normal force. It's the table that's pushing up. Does that make sense? So I can draw that one. That's going over here, right? So we'll call that the force of the table on just a little bit of the box. Okay, that's the Fn. And this is the big question mark thing. That's what we're trying to solve. What's up?
Can I ask a question?
Of course,
Okay,
anytime.
so for this one, like, I don't know, I didn't like do all this. I just kind of figured it out because I just assumed that they were going to cancel out because that hook is 10 newtons or whatever. And so I guess now thinking about it, knowing that if it's pulling down 20, in my head, I don't know if it actually is, 20 newtons pulling down and that hook is 10 newtons pulling up, obviously it's going to have 10 pulling it up to make it not move.
Exactly. I'm just slow walking us through it.
Okay.
Your intuition is exactly right.
Okay.
And if you were doing a problem like this on a test, you would not have to spend 15
Okay.
minutes thinking through every little bit and piece. Part of it is that I'm trying to fill in all the little pieces and I'm trying to get everybody up to speed. Does that make sense? Yeah, totally fair question. Absolutely. So let's get on that train that was going to get us there. This thing here says in the picture that it's pulling up with a force. So you can call this the force of the spring scale or the force of the string or whatever, something like that. Maybe let's call it the string because the string's the thing that's actually touching, right? On the box. That one does have a fancy name, the force of tension. And ladies and gentlemen, I love the force of tension. I don't love tension. That sounds like, I love tension, right? Like I like to cause trouble. No. But I do love, I think the force of tension is really interesting. I have had a lot of students that are really perplexed by it. We're not really going to spend a lot of time with it now. We'll spend a lot of time with it in a week and a half. But I don't want you to stress out about it. It'll be fine. What we need to know right now is that it's 10. And now I'm going to write out what Maddie did in her head and what many of you probably did in your head, but I just want to be as explicit about it as possible. So I'm going to write out the sum of the forces because it told me in the book. It has a little arrow that says 10. So yeah, so we just take him at his word. I'm going to write this out just to like make my heart happy here. I've got the force of tension pulling up I've got the force normal pulling up, and I've got the gravitational force pulling down. And what do those three forces have to add up to be? 0, he says with confidence.
Is that because it's not moving?
Because it's not moving, which means it's not accelerating, which means the net force has to be,
0.
yeah.
No, see, I didn't know that.
Oh, well, now we do. Yeah, is that okay?
Yeah.
Is that better? Yeah. No, and that's totally fine. That's why we do this, right? We got to learn. We practice and we learn. 0 newtons. All right. So now, again, we're kind of walking this through, but we're going to get it. This one is 10 plus Fn. This is like pre-algebra stuff that you did when you were little. Minus 20 has to add up to 0. And 10 plus something minus 20 has to add up to 0. And our brains tell us, or we do the algebra to figure out, that Fn then has to be 10 newtons.
So that's why it's equivalent.
All of them are 10. I mean, that would be the short answer, right? They're all 10.
Oh, is it because you're both set and like they're all at rest, so they're none of them are moving?
Yes. So they're all at, let's use our fancy word,
Equilibrium.
they're all at equilibrium, right? Yeah, that's our fancy way to say it, but yes. Is that good? That was a long answer to a fairly simple question, but I hope that you were with me there because there's a lot of good stuff in there. Okay. Life is good with 21? 26. Let's take a look at 26. 26. Consider two forces, one having a magnitude of 20 newtons and the other having a magnitude of 12 newtons. What is the maximum net force possible and what is the minimum net force possible?
I guessed on this one and got it right.
What? That's exciting. Congratulations.
I don't know.
Okay,
I
so
don't know.
let's think it through thoroughly and make sure that we understand it so that if you had something like that on a test, you could get it right with confidence and not be like, I don't know if I got it right. All right, so two forces and there's an object. I'm going to assume there's a little, come on team. Oh, friend, come on. Oh, see, it did this yesterday too. I don't know why. There's my object. I've got two forces acting on it. I'm going to put one of them in there just so that I've got it so I know what's going on. I'm going to say 20 newtons is pulling, I don't know, we were looking at it from above. It'll make me cranky. Newton force. I'm looking at it from above, so it's like sitting on the floor. I'm not going to worry about the floor and whatever. Okay?
Wait.
Is that okay? No? Why are you unhappy?
Now I'm confused.
I drew mine with the arrow up.
Or you're being
Why is
pulled
it to the
up.
side?
I don't know, because I had to pick a direction. What do you want? Yours up? So what I don't want to put it, I don't want gravity involved.
Oh, that's why you did that.
I don't want gravity involved. So what I'm doing literally, like if let's say I put some ropes on my Kleenex box, because why wouldn't you put ropes on your Kleenex box, right? And I'm going to set my box on the table. And then I'm going to let Tatum pull with one rope. Okay. And I'm going to let Maddie pull with the other rope. Okay. And we're going to see what happens. So one situation might be that Tatum pulls this way, right? With 20 newtons of force. And maybe Maddie pulls this way with, what was it, 8 newtons? 12 newtons? Don't sell me short. Yeah, 12 newtons. I had the 8 in my head. We are smart, right? Okay. 20 newtons this way, 8 newtons, 12 newtons this way. What's the net force? 8. Is that okay? 20 pulling this way, 12 pulling that way. Let me just draw it. So that's what my picture is here. So there's Tatum and there's Maddie and there's all the fun that's happening. So there's the 12 newtons. Okay. But what if Maddie wants to be ornery? She could be ornery, couldn't she? Maybe she wants to pull it. So now you're going to be mad at me because you're like, I didn't do this at all. That's okay. We're just talking. 20 newtons of force. What if the 12 newtons goes this way?
Is it just 20 newtons?
12 plus 20.
Well, what's the net force in this one? What did we just say? 8. Right.
That's what I thought, but no.
What happens in this case?
You add them because they're both
We add them, but we have to add them based on their vectors. What? What?
That's so good.
We'd have to do, well, you wouldn't actually do SOHCAHTOA. You'd have to do the Pythagorean Theorem. But we don't have to do that because, so here's the thing, friends. Let's look at this. Let me show you the kind of like the result of all this. This is 8, right? That's like the bare minimum. Now, if we go to the other extreme, so here's my 20 still. And if I have the 12 in the same direction, so I'm just going to add them head to tail like this. Right. Yeah, and that's what you should do. But I want to make, the reason I did the middle one is to make a point. So hold on just a second. So the total force here is going to be the 12 plus the 20. So that's going to give you 32. Okay, so that's the biggest that we can get. The biggest we can get is if they work together, if they go in the same direction. The smallest we can get is if they work opposite directions. And then there is a whole slew of different options depending on what angle we decide to pull this one at. Okay, so it could be there, it is possible. I'm not going to give you this problem, but it is possible to have a net force of anything between 8 and 32 with these two forces. Because you could have Maddie pulling just a little bit like this, right? Or a little bit like this. You with me there? Okay. And so the resultant force is going to be anything between absolutely canceling out as much as possible and absolutely adding together as much as possible. Does that get you where you need to go? Janelle, does that make sense?
Mm-hmm.
Okay.
I was just confused how I got it right, but didn't know exactly how I got it.
Got it right, what? Yeah. So was there a question about this, or did I skip that one? Or maybe you're gonna have it in a couple days. I don't know. There might be a question somewhere out there that you have to do at some point in a while that says something like, is it possible to have a net force of 7 with a force of 10 and a force of 2?
Yes.
And you would need to figure out if it is or is not. Are you with me there?
It is, right?
What's in between?
Because the minimum is 8 and the maximum is 12.
Wait.
Wait, then no, it's not.
Wait.
I thought I saw something.
I didn't, yeah, but okay, so let me back up.
Can you repeat your question?
I will.
Yeah.
I'm going to
now
change
I'm
the
gonna
numbers
figure
just to make
out.
it better, okay?
'Cause I can't.
So is it possible to have a net force of, let's say, 9 with a force of 10 and a force of 2?
Yes.
If I have 10 going this way and 2 going this way, my net force is
Wait, only one this way or like
in any way.
Yeah, 8 and 12, so yes.
So yes, it's in between 8 and 12, so yes, you can do it. Yeah. Does that make sense?
Mm-hmm.
Is that okay?
Mm-hmm.
Yeah? Yeah? Yeah, you good? The quiet ladies over there? You guys are okay? Yeah? Okay, sweet. All right. Shall we move on?
Mm-hmm.
Yes, please.
Yes.
All right, let's get done with that. All right. I'm gonna do a ranking task. Whoop, whoop. That'll wake you up a little bit, maybe. Hopefully, maybe not. I don't know. We'll see. Here you go. Take a look. Those pictures are pretty cool, huh?
Wait, what is RF?
The resistive force. Like a friction, I think. Water friction.
is this on the homework or is it just a question?
This is just a question.
I don't like this question.
The resistive force would be resisting the motion. So the resistive force would be going that way. You're ready to talk at your tables? Yeah, scattered table, you guys need to come together for this little moment in time. Go ahead and have a conversation, go.
Absolutely no idea.
Yeah.
I was thinking
Do you have any idea?
A equals D is greater than B, which is greater than C.
B would be greater than, because the resistance is greater than it's going to say.
I don't know what I said, right, there's this versus less than or being seen to the greater.
So accelerate, but it is like moving. Oh, yeah, I guess, yeah, no accelerating.
Because,
Yes, I'm saying so.
yeah, because the resisting force
So
is
then it
stronger,
would
so
be.
I guess.
Oh, zero.
so you have a higher.
I'll go with you. My estimation is bigger numbers.
No, that's like pretty much.
I'll go with you. C is greater than D, which is equal to A.
But I think it's.
What about B?
Right. Oh, sorry. C
But
is
would
greater
the friction stuff, would it make it like,
So
not, it would accelerate, but
Equal to
like,
B,
like,
C
you
greater
know what I'm
than
saying,
D.
like it'll slow it down.
Yeah, right.
You know what I'm saying?
Oh, sorry, which is greater than D, which is.
But if it's slowing it down,
That's
then
what you mean,
the
yeah.
speed starts slowing down.
But I like.
You know what I'm
That's
saying?
how it
You guys
says,
like
it's going this amount of speed with this amount of force.
That's, I know.
That's C, B, and A, and
A in the air, yeah, okay, that's what it is.
I got it.
Through the whiteboard over by Gerald, you guys can write it down.
The same as the resistance.
Is this something we should know? Because I don't remember.
I want you to use what you know so far to answer it as much as you can. Does that make sense? There's a whiteboard over there by Gerald's stuff. You wanna put your answers down, make a commitment.
Yeah, you're seeing this.
It's bad.
Yeah, it's over by the,
So would it
maybe under
be,
the drag.
wait a second.
You see the whiteboard?
So would it be D
I put it there. There you go.
is greater than D? It's greater than C, is greater than C?
Which is, sorry, which is greater than A, I still think so.
No, I think D is greater than D and C is greater than A. I just think that D is greater than D and C is greater than A. I don't know the relationship between No, I don't know. C is greater than A.
You guys have something written down?
I have A last.
You have part of it? Okay, you got some part of the commitment? Do you have a gut guess for the other two? No? Okay,
Oh, no, I did have C last because.
I'm gonna move this to like, what's that? Okay, I mean, there are two possible combinations, right? All right, let's see what we've got so far. Let's see where we're at so far. Gerald, can you hold up your board so I can see what you got? C is greater than B, greater than A, equal to D. What do you guys have over here? B greater than D, greater than C, greater than A. A, oh man, do we not have any the same today? Whoa, that's a B or a D, excuse me. There we go. B, C, and so you just went with something there? A, B, but we're not sure about those middle two. All right, friends. 4 teams, 4 answers. What are we gonna do about that?
I am so confused.
Let's read it carefully, shall we? We'll read it together. The water skiers are pulled at a.
The keyword in there is constant speed.
The keyword is constant speed. Good call. Blah, 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 blah. Rank the magnitude of the net force. I'm going to highlight those two things. I'm going to let you talk for another 30 seconds.
No, I think it could be 0 too because.
Talk. Talk, 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 talk.
Because if it's not accelerating.
Talk, 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 talk.
Some of the forces should be zero. And is that what net force is?
Because they're all in constant speed and acceleration.
Maybe they're not all zero, maybe they're all the same.
Magda, what's the matter? What's the matter?
She's in a great.
I can't, she says. I know, right? I'm so there with you. But, you know, we might as well do physics while we're here. Like, what else are we gonna do? Yeah. All right. Where are we at, friends?
I think we should go over it.
Let's talk this through, yeah?
Yeah.
All zero.
Constant speed, ladies and gentlemen. If something's at a constant speed, tell me what that means about its acceleration.
Not accelerating.
Not, right? It's not accelerating. To all of my Newtons out there, people that I like way more than Isaac Newton out there, right? If it's at a constant speed, it's not accelerating. If it's not accelerating, tell me about the net force.
Zero.
It's zero.
Well, that was interesting.
Oh.
Girl.
Are we okay?
Oh, I was agreeing with you for the most part. I was just, I didn't know.
All zero.
You didn't say anything.
All zero. I'll go through it one more time. I'm gonna go back to my sheet that maybe I wrote down somewhere. Where did I write Newton's laws? Were they here? Nope, wasn't there. It must have been up here. Yeah, there it is. Nope, nope, nope. Come on. Come on, Carbling. Where are we at? Nope. Here it is. Newton's first and second law of motion. Boom. This is it. If the net force is zero, then the acceleration is zero. It goes the other way too, though, right? If the acceleration is zero, meaning that the objects are at rest or moving at a constant velocity. Janelle was right. That is the key word there, right? Constant velocity. Constant velocity means that acceleration is zero, means that the net force acting is zero. So then you could take it one step further if you wanted to. And I'm not saying you want to, but if you wanted to, on this question, you could ask, what is the force with which is it a boat or speedboat is pulling on each one? Could you rank those? The force with which the speedboat is pulling? Like in this first one, it's got a resistive force which pulls this way of 750 newtons. The boat's pulling on it this way, right? How hard is the boat pulling? 750 newtons. Okay. So if the question had said rank the magnitude of the force of the speedboat on the water skier, then somebody may have been right. I don't know. I didn't actually go through that. A and D would be the same, and then B and then C. So this was right. So you answered the correct answer to a different question. My guess is that everybody answered the correct answer to some question there too. I don't know, but is that making sense? Okay. Because the speed is constant, we know that the net force is zero. Got to reiterate that in our brains. Okay. Question for you. Are these water skiers at equilibrium? They are. It's weird to think about something moving being at equilibrium, but it is. Okay. They'd be either sinking or they'd be accelerating one where, yeah, they'd be accelerating in some direction. Yes. Yeah. We doing okay? Everybody happy? Yeah. Okay, we're gonna do one more question. Well, one, maybe two. We'll see how we do. Well, then it's gonna be about time to go. We got 10 more minutes, so you know, we'll see. We've got I've got two things I want to do. I really want to do this one though because you are going to do 46 for homework. So I wanted you to see 45 and for us to talk about 45 so you understood it. So there's a situation here. So this is like a person who's standing on a platform and maybe washing windows, maybe painting, I don't know, doing some sort of acrobatics that I don't really want to think about because it seems kind of scary to me. Okay. It says that the painters shows a painter's staging in mechanical equilibrium. The word mechanical, has no real meaning here that's going to change our understanding. So we just kind of read over that word. We say, oh, but it's an equilibrium. Equilibrium means what? It's balanced and net force is 0. So we're just going to make a little note of that. Oh, by the way, the sum of the forces has to equal 0. That's good to know. The person in the middle weighs 250 newtons. And the tension, so we're not going to get stressed out by the word tension, right? We're just going to keep in mind, oh, it's just a force. It's just the force of the string. That's all that tension is, force of the string. On each ropes are 200. The question is, what is the weight of the staging or that wooden thing? Can you figure that out?
Is it 150?
Oh, I don't know. Let's figure it out, maybe. That's what your gut is telling you? Yeah, can you walk us through where your gut's coming up with that from?
Okay, so if it's at equilibrium, would they both, like, the arrows going up and the arrows going down need to equal the same thing?
Mm-hmm. They have to all add up to be 0, yeah.
So going upwards, they'd be 400, because 200 plus 200.
So you got 200 up plus 200 up.
Is that just showing that it's the same on both sides?
Yep.
So
So each of them is
have to
200.
add them, or can it just be?
Nope, it's 200 here, and it's 200 here.
So it equals 400.
So that's a total of 400 going up.
Why?
Because, so when you measure the tension in a rope, it's really like you're trying to figure out like how hard is it pulling? Like how hard is that rope pulling on that thing? And so it's pulling with a force of 200 newtons. You can also kind of look at it, whenever you see an arrow, you can think about that as the force, right? There's a force pulling up over here, and there's a force pulling up over here. Is that okay? Okay, keep going, Janelle,
Okay, so then.
if you want. Sorry, I don't want to put you on the spot.
So there's 250 going down,
Mm-hmm.
and so that would be almost like, yeah, minus. So then you're still missing 150 to add up to that 400. So that's kind of where I got that.
Mm-hmm. I guess they use a W in the picture, don't they? So those things have to add up to 0. So 200 plus 200 is 400. 400 minus 250 is 150. So 0 has to equal 150 plus a negative of his weight, right? So that means that his weight must be 150 watts. Newtons. How are we doing? Is that okay? Yeah? Can you tell me what his mass is?
And kilograms?
Yeah.
We have to do the whole.
You really want us to do all that work?
So wait, don't we just have to?
So we do 150 divided by
Oh.
9.81.
All that work?
Just divide by 9.81, yes, that's what you need to do.
15 point, what was that, something? 15.29 kilograms. Okay, just, you know, pointing that out, that's interesting what that looks like. Question?
Like, what, they wanted the weight of the staging?
Yes, so the staging is just, oh, you know, I should, that was not his mass. That's the mass of the staging, I got confused. But that's just like the wooden beam that's going across here, right? Because the wooden beam has some weight. So those strings aren't just holding up the painter, they're also holding up the, whatever that is, that wooden construction, yeah. Does that make sense? Yeah. How are we doing, are we okay? Yeah, yeah, okay. Here, do you want to just do 46? I'll just tell you what it looks like and then you can do it and you can write it down and be done with it for your homework. Does that sound good? I'm going to draw it because I don't have it pictured, but I'll just draw it real quick. Here it comes. And then you can do it because you got 5 minutes and then you'll be done with 46. Fantastic, Miss Carbling. That sounds great. That's what you said, right? Same situation, but instead of just one painter, now we've got 2. There's painter number 1, who's got a weight of 250 newtons. And painter number 2 is a little bit bigger in some way and has a force. I should draw the arrow just a little bit bigger. Of 300 newtons. This going up is 400 newtons. And this one, it tells us that the weight of the staging is 300 newtons. My arrows are not very good. What do you think they want to know in this one? Yeah, the tension in this. That's what they're looking for. So there you go. That's something to do for a moment. If you had a problem like this on a quiz or a test, probably just writing down an answer would not be sufficient, right? Really? I know. It's wild and it's a new Miss Carveling,
I
right?
could just get it in my
Isn't
head.
it just 450?
I don't know.
Yeah, that's
Is
what I
it?
got. And the answer's right. I just checked it.
There you go. Ding ding. But you know, just saying.
I mean, I can explain it, but like, I don't think drawing out the whole picture thing.
This is what I want. That's what I want. So when you turn it in to get a stamp on Monday too, then I'd want to see something like this. And then you don't have to write all of this work. Like I don't need to see all of your arithmetic. That I'm not concerned about. But I do want you to know that the sum of the forces is equal to 0, and that's where that comes from. Does that work? Okay. I'm gonna move this down just a little bit in case you need to see that all.